This video is a quick exploration of how we can use tangent lines and secant lines to explore if a derivative even exists, and the fancy word for that is differentiability. So here we have the definition of the derivative, and we're taking the limit of the difference quotient, and we can interpret the difference quotient as the average rate of change, or more importantly, especially for us right now, slope of the secant line. Okay, so if h is approaching 0 from the left, we have that piece of information. We also have the information about the base point, that we want to be centered at the point 1. So we're investigating what is the derivative when x is equal to 1. But when h is approaching 0 from the left, we will be doing things like 1 plus a negative 0.001. So we're going to be looking at secant lines built on the left side here. And because this is a linear function, the secant lines are going to overlap that part of the function exactly. And so we see that all of the secant lines have a slope of 2 units up and 1 unit over with a negative. So the answer would be -2 for the slope of the secant lines on the left side of 1. Now, if we look at h approaching 0 from the right, those would be positive h values, so doing 1 plus 0.01. So our other points are going to be on the right side. And those secant lines all line up and overlap the function because, again, that piece of the function is linear. And here we have up 2 units over 1 in the positive direction, so that slope is a +2. So it looks like the secant slopes from the left are -2, the secant slopes from the right are +2. Or from a more just strict perspective, the limit as h approaches 0 from the left of the average rate of change is -2. The limit as h approaches 0 from the right of the average rate of change is -2. And since -2 and 2 are not the same, what does that tell us about the two-sided limit? That says the two-sided limit does not exist. So there is no derivative at a corner. Okay, so that's kind of one of the big key things about differentiability, is that at a corner, there's no derivative. Moving on to the next example, we can do the same thing. So if we are coming at 0 from the left, we're going to be the left side of our base point. Our base point in this case is -2. So here's -2. Here's the point that I always want to have my secant lines passing through. And then if h is approaching 0 from the left, I'm going to pick points over here. And then I can draw some secant lines, and I can notice that those secant lines have positive slope. We're kind of like, what is happening as we approach? So I'm going to draw a secant line with this tool, but I'm going to be able to hold it up so we can see several secant lines. So notice the point of intersection with the curve. And as I move the cursor, what I'm doing is letting those secant lines, the second base point, get closer to the first. In other words, I'm letting h approach 0 from the left. Notice those lines are getting steeper and steeper and steeper. Okay, so I could draw a line there. I could let it get even steeper. I could draw a line there. I could let them get even steeper. And so the closer that my two secant points get, or the closer that h gets to 0 from the left, the steeper those lines get. Positive slope but steep. So we could say infinity would be the answer to that limit. And if we come from the other side, similar ideas. These secant lines are getting steeper and steeper and steeper, but they are negative valued. So we could say they are tending toward negative infinity. And then again, because the two one-sided limits do not agree, we'd say the two-sided limit does not exist. So the takeaway is there is no derivative at a cusp. So this is a cusp when the curve kind of does that sort of shape. We call that a cusp. And there's no derivative at a cusp because the slopes from the left and the right do not equal each other. Here's another example we can play around with. So again, our base point in this case is -3. So we're investigating the existence of the derivative at 3 as h approaches 0 from the left. we'd pick points over here for some secant lines. And we'll notice those have negative slope, but they are getting increasingly steep. So that would be negative infinity for that limit. And as h approaches 0 from the right, we're on the right side. So you can draw some secant slopes that are, again, still negative in value, like they're negative slopes, but they're getting increasingly steep. Okay, so the limits agree in this context, but they're not actually numbers. So we're still going to conclude does not exist. Okay, and if we were to try to draw a tangent line in here, we would call this a vertical tangent line, straight up and down. So we can actually draw the tangent line. So in this case, we can actually point to a tangent line. In the previous examples, we couldn't even point to a tangent line. We didn't even know where the tangent line would be, right? So here we can at least sketch it. But this is a vertical line. And what do we say about vertical lines? The slope is undefined there. And that's just convention. That's a convention that mathematicians set up, that if we're oriented this way, we have 0 change in our horizontal and an infinite amount of change in our vertical, and infinity divided by 0, just we don't deal with that. We call this undefined. So we'd say there's no derivative at a vertical tangent. Okay, and then just a quick little summary slide here. There are, so where non-differentiability, differentiability is tied to difference quotient, it's tied to the derivative existing. So non-differentiability would be the derivative does not exist. Derivatives will fail to exist at corners, cusps, and vertical tangents. Those are the ones we talked about already. The ones we haven't talked about are just discontinuities. And so here's an example of a jump discontinuity. If we are approaching 0 from the right, all of the slopes are 0, right? So that one's easy. Slopes equal 0. But the thing that it gets a little interesting is what happens when h is approaching 0 from the left? It's really tempting to say, oh, well, those slopes are 0 too. And 0 equals 0, so why is there not a derivative? But we have to be really careful because remember we're doing our secant lines. What's the base point in this case? The base point is up here. Okay, so all of our secant lines have to go through that point. So if I pick an h, maybe it's over there, and I draw a line through those 2 points, it looks like this. And I let h go to 0. So that's the little trick, is like remembering that we have to pass through 2 points, and one of the points is actually on the other line. So as h goes to 0, those slopes are positive valued, but they're approaching infinitely steep. So we'd say the slopes are approaching positive infinity. And there we see the discrepancy. The two sides do not line up, and therefore we get undefined for that limit. Therefore, the function is not differentiable to jump discontinuity. But it's not just jump discontinuities, it's all discontinuities. So a function is only differentiable where there are no corners, no cusps, no vertical tangents, and no discontinuities.